Welcome to lecture 20, which is on remote sensing satellite orbits. So, in this lecture I shall cover two major kind of orbits in which the satellite moves and provide us very useful data products. So, let us begin with this lecture. Satellites are any object which revolves around a planet. That is a basic definition of the satellite. And we have two broad categories of the satellite. As you can see, natural satellites are there, where we are talking about the various planets, and artificial satellites are there, where we are talking of the man-made satellites. So, we will talk in this lecture about those artificial and man-made satellites. So, these satellites are launched to carry out a wide range of tasks for us. So, they will provide images at different resolution, at different coverages, and also the other category of the satellites, they are used for telecommunication purpose, relay the signals for education purpose and so on. So, if we focus on the orbits of the satellite, any satellite will actually circle the earth using a path which is called orbit. So, this is the path which is followed by a satellite, and this is called the orbit, this is the earth surface. So, the satellite is moving around the earth. Now, when they are moving around the earth here, they are following actually certain laws, and this is called the Kepler's law. So, there are three very popular Kepler's law which the satellite, when it is moving in the orbit, they are bound to follow those laws. And the parameter of the orbit, we can define this elliptical orbit with some parameters, and the, for example, the height is very important, the inclination and the speed of the aircraft, the satellite which is moving in the orbit. So, there are basically now two categories, two broad types of the orbits which we will discuss here. One is the polar orbit, where the satellites are moving in very low altitude, and the other one is the geosynchronous orbits, where the satellites are moving away from the earth. So, these are the two broad categories, polar as well as the geosynchronous orbits. So, earth observing satellites, which we call as the remote sensing satellites, they are using a wide range of the orbital altitude. So, they are available to us at different altitude, height from the equator, inclination at different inclination, the angle the orbital plane is making with respect to north-south line or with respect to the equator, depending upon what type of observations we are taking and what is the time interval of those observations, the temporal variation of those observations. These satellites can give us very highly accurate data, long term measurements also of the globe. So, we can get repetitive data and very accurate information about the entire globe. So, let us see the characteristics of the polar orbits. So, here in the diagram, the polar orbit is shown, and they are available at different altitudes. Popularly, they are also known as the Sunsynchronous orbits. So, synchronized with the sunlight. So, that is like a Sunsynchronous orbit, because they are using the natural light of the sun. Now, they are moving from pole to pole. They are actually, the orbital plane is passing through the pole, close to the pole, and that is why popularly they are called the polar orbits. Their altitude is low. They are flying at different altitudes, and at low altitude the signals are very strong. So, higher the altitude, more will be the atmospheric losses, as we know from our previous knowledge. So, since the altitude is low for these satellites, so we get very strong signals, reflectance characteristic. Temporal resolution, if we are talking about that, that is varying from 14 days to 35 days. It may be lesser also. But this is a normal range, 14 to 35 days you will get the repetitive images of the same area again. So, these polar satellites, when they are moving in the orbit continuously after their launch, they will provide the coverage of the whole globe at regular interval of time. So, we have to understand how we are getting the global coverage at regular interval of time from the polar satellites. There are some examples. The list is very long, but some of the very popular satellites, polar orbiting satellites, which we will further discuss and show the images. These are very popular satellites people have used world over for some application or the other. Now, the second type is the geosynchronous orbit. Geo means earth. So, the speed is synchronized with the rotation of the earth. So, that is why they stay over the same point on the earth. When they are launched at a certain coordinate system. Say here the satellite is launched in the geosynchronous orbit, their coordinate is fixed, and this satellite would actually move with the earth rotation speed at the same speed as the rotation of the earth, and cover the same piece of the globe throughout its life. So, it is not covering the whole globe, but it is covering only the part of the globe, the area, and continuously it is monitoring that area. So, these orbits are called high earth orbiting. So, they are from high to very high orbits. These satellites are completing the one revolution in 23 hours 56 minutes in order to maintain the continuous positioning at the point where it is placed. Some examples of Indian satellite, for example, is INSAT, the geostationary operational environmental satellite is known as the GOES, then there are the Meteosat satellites and GMS and so on. The list is also here very long because many countries have launched their own geosynchronous satellites. So, if we typically see the orbit of a polar satellites or sun synchronous satellites, they are at a low altitude. The angle of inclination is also with respect to north south line is plus minus 3 degree, very small angle, and this is the strip. It is showing one strip on the ground. So, area covered on the ground is shown by the white strip. When the satellite is moving, it is looking at a certain area at any given instant. From north to south direction it is moving and continuously imaging the area underneath. So, the strip is that area which is actually totally scanned by the satellite when the satellite is moving. So, these polar satellites or sun synchronous satellites are actually designed in such a way, their speed is synchronized in such a way that their orbit passes over the same place at the same time of the day. Meaning of that is the normally along the equator the images are taken in the morning hours when the effect of shadow is less and also the environment is clean, pollution free. So, it will pass at the same place again at the same time, almost at the same time in the morning hours along the equator. So, this has been designed in such a way and it has been kept intentionally also because so that the illumination conditions remain same. If I have the temporal images taken at time t1, time t2 and time t3, I will have the same illumination condition if the image is taken of the same area in different years or maybe the successive days. So, this is the characteristics of the polar satellite, and these satellites they are circling the earth, they are continuously moving the earth in the north south orbit, north to south orbit, and this orbit is passing very close to the pole. So, this we have to remember that when the satellite is moving from north to south, it is trying to take the images of that area because that is the sunlit part of the earth at that time. Now, the height of the orbit, it is varying and it is typically 600 to 800. This is the typical value, but you may find some of the satellites are much lower altitude than 600 and some are slightly higher altitude than 800 above the surface of the earth. So, they are viewing the earth surface directly below it. So, there is no of nadir right now capability, just whatever is the area just below when the satellite is moving, it covers the area of the earth surface. Now, when the satellite is moving from north to south, what it is doing, it is actually imaging the sunlit part of the earth. So, this is very, very important because we are actually working in the passive mode. So, passive sensors are there which are measuring the sun energy. So, which the part of the sun lit part of the earth which is there, it will actually take the reflectance, it will record the reflectance part of that. So, we are using sun as the source of illumination for polar satellites or sun-synchronous satellites. And from north to south journey it is taking, because half part of the earth is sunlit and half part of the earth is in shadow. So, north to south part onward journey, it will cover the earth which is sunlit part of the earth. Now, when it is taking south to north journey, okay, which is the other part of the earth which is in the dark. So, half part of the earth is sunlit and half part of the earth is dark. So, when it is moving from south to north, the passive sensors will not record any energy because nothing will be reflected to the sensor. So, in that case, we take help of some of the active sensors, what we call as the thermal infrared sensor or the microwave sensors, because they can capture the emitted radiation from the earth surface. So, here we are using the capability of those sensors where emitted radiations could be captured during the low light time, during the night time as well. Now, if you see the polar orbits which are moving, here you can see strip number 1 which is covered, strip number 2, strip number 3, strip number 4. How the whole earth is covered? Because the satellite is continuously moving and there is a rotation of the earth. So, earth is also rotating. So, by the time the satellite completes one rotation, some portion of the earth has already rotated, it has moved below it. So, below that a fresh part of the earth will come. So, that is how it is happening here also, that we get 4 strips for example shown, and it is continuously scanning the whole of the globe, because the rotation of the earth will continue from west to east, and there will be a complete movement of the satellite also from north to south. In the orbit it is moving continuously. So, north to south journey, it is all scanning the whole surface. So, this way the part which was under shadow, which was not sunlit part, after some time that part will come under the sunlit part and sunlit part will go into the shadow part. So, the shadow part will be covered after some time when it comes under the sunlit portion. So, that way the whole of the globe is covered due to the rotation of the earth from west to east, and also the rotation of the satellite in the orbit from north to south journey. So, in few days, in few weeks, this repeat period is also varying from satellite to satellite. So, the whole of the earth is covered. Now, if we have 2 to 3 polar orbit satellites, the same series of the satellites or 2-3 satellites from different countries, polar satellites which have been launched, if we take them together, the temporal frequency we can reduce. So, we can get more frequent data if we take the polar satellite data, let us say from LANDSAT and from IRS, from SPOT, then we can have very data which is basically maybe every day or every alternate day. So, we can actually reduce this temporal frequency of the data when we consider it from 2-3 satellites. Now, when this satellite is moving in the orbit, there is a term which we use in remote sensing, it is called swath width. And in this diagram here, the swath width is shown. So, swath width is the width of the strip on the earth surface. When the satellite is moving in the orbit, it is covering a certain width on the ground, and that width is called the swath width. And this swath width is very important because the swath width will also determine the size of a scene. So, normally a satellite scene is normally take a square shape. So, whatever is the, if x is the swath width, then in the perpendicular direction also it will take x. So, dimension of the scene will be x multiplied by x. So, that is what it says, that the area covered by one scene can be calculated swath square. So, we are taking that dimension as the standard dimension to segment the whole area into the number of scenes. So, this swath width will also vary, it is not a fixed, it is not a constant quantity for all the satellites, for all the sensors. So, it will vary also in of the orbit type, also the characteristics of the sensors which we are using to capture the data. Now, this diagram shows that different satellites have different swath width. So, x axis is showing swath width up to 200 kilometer, and then there is a resolution on the y axis. So, there are satellites which are giving us a small area is covered, but they are giving a high resolution images. So, we know that the area covered is small, the resolution becomes very high. So, you can see for example, these satellites, Iconos satellite or Orbu satellites, they have a smaller swath area and very good resolution is there. Whereas, if we talk about the spot satellite, and if we are talking of the LANDSAT satellite, the swath width becomes more and more, and area covered becomes large, and obviously the pixel resolution will become medium kind of a resolution for LANDSAT. So, this diagram shows that as the swath width is increasing, the resolution becomes poorer and poorer. So, we have to see if we want high resolution data, the area covered in one scene will be very, very small, and then probably we need very large number of scenes in order to compile the mosaic of the whole area and to carry out the planning for the entire region. Then there are successive orbits. So, I have shown you the orbits in on a globe. So, if I for example open the globe, if I show that globe into a two dimensional piece, so we get something like this figure. So, the satellite is moving in the orbit, and if I want to show you that globe because of the nature of the curve of the earth surface at the north pole and the south pole also, you will get this kind of a figure. You get quite a good overlap, north pole and the south pole. And then the orbits are shown here. So, one is the orbit in the north-south journey, and then the opposite what you see is the south to north journey when it is taking. So, how much is the width which is covered on the ground. So, we can see from this kind of a orbit, successive orbits, if we could give some number to these orbits, so that the orbit is identified, which orbit the satellite is moving at a particular day. So, we can see this kind of a diagram where a number of orbits are there to complete the whole earth by a particular sensor, by a particular satellite. But near the pole, then we will find that the overlap is there, because the area covered along the pole becomes much smaller. So, when the area is much smaller, there is a lot of overlap available in those images. So, we are getting a lot of overlap in those images near the poles. But far away from the equator, if we go far away from the equator, we can get very less overlap between the two successive scenes. So, we cannot use them for creating a 3D model and so on. So, our repeat cycle would increase if we are working in the area near those poles, because we can get the very frequent images with the successive overlaps between those two images. So, now this orbit path has been given a number. So, the next term here which is important for us to understand is the path and row number of a particular scene. So, when the satellite is moving in the orbit, that is the path of the satellite, this particular path is given a certain number. So, next time it moves, it is given another number, so that we can identify in which particular path which portion of the earth has been covered. So, we define them by a unique number, it is called the path number. The orbits we are defining by a unique number. And what is the row number? Row number is the length of the scene across the orbit path. So, I have shown you the Swath width. So, across the orbital path, if we divide that entire strip into different rows, so that we can segment the continuous signals which are received from the earth surface to the satellite sensor. So, we have to divide that strip into certain rows now, and that row number is also given so that we can define a particular scene. If we want a scene for Delhi area, then there is a specific path number and row number under which Delhi scene would lie. So, normally this path and row number map is very useful in order to locate a particular scene from a particular sensor, so that it is correlated with the geographical location of the place. So, these are unique numbers. Path and row numbers are the unique numbers where the entire world has been divided into some kind of a grid. So, the whole world is divided into path and row numbers for different satellites. So, this path row map, if I say, is different for different satellites. So, I have to consult, if I want to order the satellite data for a particular sensor for a particular satellite, then I have to consult the path-row map for that satellite and that sensor also. And it is really very significant when you are placing the order. If your path and row numbers are not correct, maybe you end up buying the satellite data for some other area. So, we have to correctly identify these path and row number so that we can identify a scene which covers our study area. So, this is the example of the LANDSAT only. So, it is a path row number of the world map. So, the whole map has been divided into the satellite orbital path, and a perpendicular to that is the row number. So, you can see a grid. So, you can see, for example, a grid. So, this is each grid has a unique number now, and they are called path and row number. So, there is a number here and there is a number here on this map. So, like the coordinate system, we can find out path and row of any particular area. If I show you the enlarged view of a small part, Nigeria. So, this is the LANDSAT path and row number map. So, you can see in this diagram, it is starting from 185 path to 191. So, all these strips covered on the ground by one rotation of the satellite is showing that. And then we have the across is the row number. So, here you can see that row number is ranging from 51 to 57, and one scene is almost square, and there is a small overlap. You can see this overlap between one scene. This is the overlap here, this is the overlap there. So, very small overlap is there between the adjoining scenes. In the adjoining path and adjoining row, there is a small overlap. So, these are the path and row number which you can locate a particular area. So, if you want any scene of a particular area, so this path and row map would help us to define those numbers. Now, what are the uses of the polar orbiting images? We are using for mapping the earth resources. This is the very popular applications which has been used worldwide by maximum number of people to carry out the resource mapping with the help of these polar orbiting satellites at different scales. Mapping the infrastructure. So, we can map the infrastructure because we can see that infrastructure now from a better resolution satellite data. We can monitor the area because we can get continuous images of the area. So, we can monitor the area, we can update our maps, topographical maps with the help of these images, or we can develop any number of applications, use these images along with the other data in GIS environment to develop the application. So, there are very large number of users and large number of applications of the polar orbiting images. Well, the life of a remote sensing satellite when it is launched up in the orbit. So, normally the design life is 5 years normally, but you can see that this diagram shows that from 0 design life and it is going up to that 16 for example or 20. So, some satellites are working, they are operational well beyond 5 years. So, design life is 5 years, that means the next satellite has to be ready for launch before the expiry of the previous one, so that the continuity is maintained. But many satellites, as you can see, actual life is given on the y axis. So, here you can see that the many satellites have performed much more than that what was the design life of the satellite. Now, geosynchronous satellites are moving in the equatorial orbit. So, that orbit is very far from us, approximately 36,000 kilometer from the equator. So, very far away from the equatorial plane. So, when the satellite is up very far, it will cover large area. So, there is a relationship, it is obvious. So, we have very high view, very large view which is covered by these satellites. So, these satellites are moving in the orbit which is parallel to the equatorial plane. That is the property of this. So, when it is moving parallel to the equatorial plane, it is moving with the same speed as the rotation of the earth. So, it will keep on taking the image of the same area throughout its life. So, you can see here the satellite is moving in the orbit and there is a rotation of the earth also about its axis. So, the earth will nearly in 24 hours complete one rotation. The satellite will also complete one rotation in the orbit in this 24 hours. So, that means it will keep on looking at the same area. As you can see from this diagram, the satellite is looking at the area which is shown by a circle here. So, throughout its life, it will keep on scanning that area and continuously send the images of that area. So, if we want global coverage, then probably we need several these satellites at different locations. So, few satellites if we have can provide the entire global coverage. So, I will have the images of those satellite, images from several of such satellites. But the advantage of this is the constant monitoring of the area, and that is very important when we are doing some kind of a disaster management planning, when we are developing some kind of a warning system, we need continuous monitoring of the area. Apart from this, these satellites are very useful for telecommunication purpose and other purposes as well. So, they are very useful to us in the communicating. So, we can see various geosynchronous satellites are there. This is the globe here, and then you can see that very large number of satellite geosynchronous satellites have been launched at different latitude and longitude. So, different values these satellites are launched, and they are continuously now taking the image of that particular region, their field of view. So, we get the continuous data. We can actually use that data for weather forecasting, we can use that data for meteorological satellite. For example, on our Indian television we see the weather forecast. So, this weather forecast, we see a big image which covers a large area, India and surrounding continent. So, that is from INSAT, from our geosynchronous INSAT satellite. So, very large area is covered, and we can get images every 15 minutes, every 30 minutes if you want. So, what are the uses of these images? You can see communication, very big use, then the transmission of the information. Program telecast on the television we can use for weather forecasting, we can use for mapping and monitoring work of the large area, and particularly the disaster related activities which are to be monitored continuously. So, there are various uses of the data from these geosynchronous satellites as well. Now, if we summarize, what is the utility of the polar satellites, what is the utility of the geosynchronous satellites. Polar satellites are providing us medium to high resolution images after every few days, and those images are very, very useful to us to carry out the resource mapping, to update our maps, to monitor the whole of the globe, because we get lot of data after certain interval of time. But the geostationary satellites, the resolution becomes poor, maybe 1 kilometer or maybe more, 1 pixel size. So, you cannot carry out the resource mapping from that. You can't see those small features from that. You can see the broad features only from those satellite at that resolution. So, but you can get very frequent, that is the advantage. Whenever you want, you can have that image very frequently, and you can prepare small scale map from that. You can prepare a small scale map, you can use for climatic change, disaster management, communication purpose, forecasting purpose. So, that is the advantage of the geostationary satellite. So, depending upon the application in hand, depending upon the objective what we want to achieve from the data, we will like to select the data either from the polar satellites or from the geostationary satellite. So, this is all about this lecture. Thank you.